Hello, I am Jacob Hughes, and this is my lab report for Physics 2212 Lab 4, Circuits. The purpose of this lab was to determine the RC value of a circuit, measure a conventional circuit, and the potential difference values, and predict the behaviors of circuits. To do this, we used Ohm's law, V equals IR. The loop rule, which is delta V is equal to 0 across a loop. Node rule, which is the sum of currents into a node, which equals the sum of currents out of a node, and delta V capacitor minus delta V resistor, which equals 0, and which is QC minus IR is equal to 0. And for the results, I got RC is equal to 5.882, and resistance 1 is equal to resistance 2 is equal, current 1 is equal to current 2 is equal to 0.02 amps. So the initial conditions of the experiment was that a series circuit of a 3-volt battery, 2 resistors with resistances of 47 ohms and 100 ohms respectively, and 2 ammeters set up. And the predicted current 1 and current 2 is found by the loop rule, which is 3 minus 47 times current 1 minus 100 times current 2 is equal to 0. Current 1 is equal to current 2. Therefore, 147 times current 1 is equal to 3. Current 1 is equal to current 2 is equal to 0.02. For parts 2 and 3, the experiment shows that the predicted value matches the estimated value of I1 and I2, and the readings don't change when one of the ammeters is inserted backwards. Part 4 is that reading the voltmeter is 3 volts and is equal to the EMF, and the reading on the ammeter is the reading on ammeter 2 is 0 amps because the voltmeter does not allow current to run through it, causing the circuit to act as if it is open. The system is the circuit, and the surroundings are everything else. So, parts 5 through 7, the sum of potential differences should be 0 due to path impedance, or path independence, and this is proven through 3 minus 47 times 0.02 minus 100 times 0.02 is equal to 0. Parts 8 through 9, the voltmeter doesn't change the reading of the ammeter because only a small amount of the current passes through the voltmeter. Parts 10 through 12, when connecting an ammeter in parallel with the 100 ohm resistor, the reading increases to 0.06 amps because there is a path with less resistance for the current flow, which increases the overall current in the circuit. The resistances are 47 ohms is equal to minus 0.96 over 0.02 is equal to 48 ohms. R 100 ohms is equal to negative 2.04 divided by 0.02 is equal to 1.02 or negative 102 ohms. I am adding decimal places where they shouldn't be. I am sorry. Resistance of the wire is equal to 0 ohms, and the resistance of the ammeter is 0 ohms. So part 2 of this experiment is as follows. Parts 1 is the light bulb starts bright and then quickly dims as the capacitor is charged. Part 2, when the light bulb is only connected to the capacitor, the light bulb is initially bright but dims quickly as the capacitor loses charge. When the battery is connected, the current is lost from the circuit as it enters the capacitor. When the circuit is only the capacitor and the light bulb, the current is lost from the circuit as it is emitted as light. The time results show that 10 ohms minus the charge of the capacitor, or 10 ohms charging the capacitor takes 2.81 seconds, discharging the capacitor takes 2.76 seconds. For 20 ohms, charging the capacitor takes 4.08 seconds, and discharging takes 4.20 seconds. So here is a table showing time versus delta V of the capacitor. As we can see here, it decreases exponentially as time goes on. And here is a graph of the data with ln of V over V naught versus time. So the sources of errors would be the inaccuracies in time measurements. And for what if I was doing this in real life with an actual ammeter, the values for current would be different as there would be resistance in the ammeter. And if I were doing this in real life with a real battery to charge a real capacitor, it would take a finite amount of time for the battery and capacitor to charge instead of instantaneously.